Good afternoon or good morning, depending on where you're joining us from today. Hello, my name is Brenda Suggett, and I'm the Executive Director of CARSP, and welcome to today's webinar, which is entitled Exploring the Use of Wireless Sensors in Pedestrian Safety Analysis. And today I am joined by two speakers, Professor Kareem Ismail and PhD candidate Salah Fakouri. And I will introduce them in 1 minute. But first, I wanted to put a little plug. If you aren't already a CARS member, I wanted to encourage you to join. This is an example, today's webinar, of our monthly webinars that we offer for free to our CARS members. And on occasion, when we partner with IT Canada, they also get the free webinar as well. So I just want to encourage you to join. There's many other benefits as well, including discounts to our conference, a quarterly newsletter, and monthly news digest. And before I introduce our speakers, I've got a housekeeping item, and I also wanted to put in a plug for next month's webinar, which is called Sustainable Safety and Vision Zero. And it is actually a joint webinar with ITE Canada. And that takes place on February 27th at noon Eastern, and it is being held by two speakers from MobiCon. So that's going to be an excellent webinar. You can check out the description of it on our website and register there as well. So today's, oh yeah, and then in terms of housekeeping, we do take questions, but we don't answer them until the end. But you can submit them throughout the webinar using the Q&A function at the bottom of your screen. So once again, you can submit them at any time, but we won't answer them until the end of the webinar. So without further ado, I'm now going to present to you our two speakers. So the first one who's going to be speaking is Professor Kareem Ismail, and he is a professor of transportation engineering in civil and environmental engineering. He obtained his PhD from the University of British Columbia and joined the Department of Civil and Environmental Engineering at Carleton University in 2010. Professor Ismail's research interests include modeling sustainable modes of transportation with a special focus on non-motorized modes of transportation, road safety analysis, highway design, and utilization of advanced sensor technology, including wireless sensors in traffic data collection. The other presenter is Salah Fakouri, and he's a PhD candidate who uses wireless sensor technology to enhance pedestrian safety. Salah developed applications to monitor pedestrian and vehicle movements to identify potential dangers and achieve safer urban environments. So I'm now going to invite Salah to share his screen, and Dr. Ismail will be the speaker.
Well, good afternoon, everyone. Thanks, Brenda, for the introduction and the invitation, and thanks, Homo, for organizing all this work. I would like to start the presentation by thanking all the attendees and giving the overview of the presentation. And then Salah will be presenting later parts of it. The title is Utilization of Wireless Sensors for Pedestrian Safety Studies, and it is done through research by myself and Salah Fakhouri, my PhD student and at College University, and a good portion of his PhD will be presented today as he nears the final stages of his studies. Also, funding is acknowledged from National Science and Engineering Research Council of Canada and from Transport Canada. The presentation is organized in introduction. We'll talk about the motivation of this work, the dreams that we have, some quick overview of previous work. Then we will move to to describing the technology as much as we can in that limited time. Also refer the attendees for published work on the subject matter. Important findings will be presented, then recognize limitations and lessons learned by ourselves and recommendations for future directions. So a quick overview about the purpose of this research. So pedestrian-involved collisions are highly risky compared to motorized modes of transportation because pedestrians are recognized as vulnerable road users. If we look at the National Collision Database, and these are numbers we pulled ourselves, we see that the number of fatalities involving pedestrians is not declining as fast as we want. The trend seems to be a little bit stable, and these are the most recent years I could find on the National Collision Database, pulled a couple of weeks ago. If we analyze this data further on the next slide, I started to ask, when do collisions occur? So if we separate them by time of the day, we'll see the majority are in dark conditions, and the second majority very close in daylight conditions. Doesn't really reveal the seriousness of walking at nighttime to pedestrians. So I tried to ask, okay, what are the odds then of the collisions being bad, which means what is the probability of being a fatality instead of an injury only? And we'll see a remarkable difference here. So in daylight, you will see that the odds are much less for the pedestrian-involved collision to be fatal as compared to injurious. And in fact, this is not an isolated trend in a particular year. It's just noticed all over the years. So walking at nighttime is quite dangerous activity. What can we do about that? This is a problem that is also recognized in the literature. Many studies noted the risk of the safety risk for pedestrians when they walk at nighttime. For example, the cited source. And walking in nighttime is also an a situation where many sensors may fail to perform very well, and probably the primary sensor, camera sensors don't perform very well in poor light conditions. Adverse weather is not only, poor light conditions, but also foggy conditions can befall pedestrians. You see here, pedestrians just appear and very close to the vehicle. So what sensors are available in our arsenal? So video cameras are ubiquitous, but they suffer due to poor light conditions and also poor weather conditions. And unfortunately, these are the conditions where pedestrians are at heightened risk, as I explained earlier. LiDAR technology is very promising, but scattering of laser light can happen in foggy conditions. Radar technology is robust, but it may not perform very well if the target object is close to the sensor and it's very large in size. Wireless sensors are fairly robust. The electromagnetic waves that we rely on, at least in this work, can go through fog and can perform at nighttime conditions. So quickly, I will present previous work by a PhD student, Shahrayar Mohammadi, and the work has been published. I tried here to calibrate scenes and improve the localization accuracy. And if you collect data from inside intersections and you have more than one receiver, in this case you have 4 receivers, and they are placed carefully, you may be able to localize the source of the signal. And in this experiment, it was Bluetooth low energy. You can localize the source of the sensor within maybe 5 meters, which can help in applications that involve, potentially safety applications. You can also detect turning movements, like we present here. However, the reliance on uh, Bluetooth Low Energy um, is helpful, but we cannot really turn a blind eye to a competing mode of communication, which is ultra-wideband. So, ultra-wideband has been touted as superior in ranging accuracy. Ranging accuracy means to know the distance between the source and the receiver. The source is a beacon that sends a signal, and the receiver, receives the signal, and they want to know the distance between them, preferably in a dynamic way. So every time increment, I want to update this distance. What is different? Just to go back, so what is different regarding ultra-wideband? By name, the bandwidth is fairly wide, so it ranges here from 3.1 to 10.6 gigahertz, whereas Wi-Fi and Bluetooth are much narrower, and they are localized at around 2.4, 5, and 6 gigahertz. So ultra-wideband has some advantages due to that. It's a technology. On the next slide, we'll see that has gone through updates. Standards have improved with focus on ranging accuracy. It's relatively new. So we see the most recent update in 2020. And there are some review papers on this mode of communication. And some recent applications as well. You see it in the cited sources. For example, the first study wanted to utilize ultra-wideband to alert pedestrians when they are walking within an intersection. Some applications focused on comparing it to other modes. For example, a well-known mode is Wi-Fi. However, Wi-Fi offers advantages, but also some recent disadvantages in address randomization. We can talk about this more. Ultra-wideband promises superior, ranging accuracy. Some studies considered non-line of sight conditions where there is no clear path between the source and the receiver. The research that Salah will present was not possible before sometime in the middle of 2022. The reason for that is that the Apple devices, for example, iPhones, have a chip, an ultra-wideband chip. They call it the U1 chip at that time. And the data was not available for developers up to sometime in 2022, where the manufacturer allowed developers to access this data. With the promise of ranging accuracy, it was very tempting to utilize the U1 chip. So we purchased equipment that allows us to range for between phone and a receiver. And Salah will be presenting some specialized developments on that. But then sometime in 2023, the U2 chip has been released, which offers further range. So it is a technology that is supported by manufacturers, and it's gaining popularity. So we thought about that, and what can we do? Can we satisfy our dream of protecting pedestrians, improving pedestrian safety? So given the near ubiquitous use of smartphones, can we do that? So quick mathematical introduction for how ranging works. If you have so-called single-sided ranging, two-way ranging, so a message that contains some data is sent from the beacon to a receiver, and it takes time to travel, and then it's received and sent back. If you want to improve the accuracy and robustness, you can repeat this process one more time, so the data is sent from the receiver back to the sorry, from the initiator to the receiver and then back. And by measuring time of flight, and that's one of the common techniques to range, then we can estimate the distance between the initiator and the receiver. What are the dreams we can satisfy with this ranging accuracy? Can we use somehow the data collected by the phone to improve safety for pedestrians, or at least gather safety relevant data? What's our safety relevant data? Can we, for example, through widespread deployment of such technology to identify hazardous locations where when people walk there, they are in close spatiotemporal proximity to motorized traffic? Can we alert somehow through connectivity drivers to an unseen pedestrian on site, unseen by the driver and or by the video sensors that require good light conditions and good weather conditions? Can we improve safety in any other ways? Can we do that using inexpensive equipment? Can we do that in real time? So the data will be processed real time and the protection can be conferred in real time. What type of spatiotemporal proximity indicators can we gather? We have, spatiotemporal proximity that asks, okay, how fast are you closing to an object and how much time is remaining? Can we also measure the retrospectively? Can we assess the temporal proximity by asking how much time elapsed when the two road users crossed path? If this time is short, then that was really a risky interaction, and vice versa. And how often can we gather this data, and what is the accuracy of such measurement? So at this stage, I'm going to hand the presentation to Salah. He will give you more detailed information about the technological part. He, as part of his PhD, and I will come later to conclude, and also we are both ready to answer your questions at that time. Salah, it's yours now.
Yeah, thank you, Dr. Karim, and thank you, CARSP, for the invitation for this webinar. So a safety application was developed to run on iOS devices and compatible with the U1 chip equipment Apple devices, as shown in the figure. So for example, the application presents the detections from all connected UWB beacons, such as fingerprints, average speed, acceleration, time to collision, mixed time to collision. The distance and timestamps are printed on the screen and stored on an external online database for near real-time and offline analysis. The application changes the background color, such as red, orange, green, based on the level of the risk. So all hazardous mixed time to collision values were between a threshold of 0 to 3 seconds. So for example, a red background color will appear when a mixed time to collision is between 0 to 1 seconds, representing a high risk situation, as we can see in the first figure. As well as we can see a notification where it shows it's a critical hazard in all 3 screenshots. The figure illustrates the setup of the equipment used in the experiments, as well as the beacon location at the right front point of the vehicle, mounted on a specific holder so that the beacon did not rest on a vehicle body. The tripod carrying the phone that runs the safety application, as well as another tripod carrying a video camera recording the experiments. The lateral offset of the phone location from the beacon mounted on the vehicle was approximately 1.75 meters. These experiments were conducted to test the accuracy of the UWB beacons in assessing the risk of pedestrian vehicle interaction. or conflict. These experiments were conducted in two different environmental settings, outdoors and indoors, for example, underground parking garage. The outdoor experiments were analyzed in relatively harsh winter conditions, such as freezing rain, snow, and cold, to cover many weather conditions. These experiments were conducted at Carleton University campus. The outdoor location was at an intersection controlled by a stop sign, and indoor location was in an underground garage, as we will see now. So the experiments were conducted at different speeds for approaching vehicle. At each speed, several trials were conducted involving a vehicle approaching the phone location along with time to collision calculations to ensure consistency of findings. The temperature indoors was plus 13, and reference points were placed as colored cones every 2.5 meters to estimate the vehicle location, as shown in the on the left figure. Two cameras were placed to record the experiment inside the car to monitor the vehicle speed as it approached to the phone location, as well as an external fixed camera to monitor the phone during the hazardous vehicle approaching, as shown in the figure A and C. So a typical trial starts when the UWB is actively communicating with the phone. That is, when the distance between them is dynamically measured. Then the car moves to the starting point, which is at distance of 25 meters from the phone, as we can see in the figure C. The car accelerates from that point up to various targeted speeds, 3 kilometers per hour, 5, 10, and 15. The driver aims to maintain the speed once it's reached and moves closer to the phone location. Figure B and D illustrate the estimated horizontal distance at trigger to be 7.5 meters, and the vehicle speed appears to be 9 kilometers per hour, as shown in figure B. And we can also see a flashing alert to alert the driver. So the first figure shows the car moving towards the phone, and this is before the notification triggers. After the phone's notification was triggered, a notification was sent to a connected smartphone or smartwatch, sorry, and the phone flashed to alert the driver. This is a video where it shows the vehicle is approaching, and we can see the flash to alert the driver. This is another video from a different angle. We can see the phone is triggering and initiating a notification to alert the pedestrian as well. This is another video from indoor experiments. This is the flash. This is from another angle. So these are some key findings: detections at speed of 5 kilometers per hour. These graphs shows the average speed, distance, and time to collision profile. It was noted that occasionally, when the notification is triggered, the average speed increases significantly immediately after, because the application records another distance within approximately 2 milliseconds. That's why we see a spike at the end of the average speed on the top left graph. These are the detections for 10 kilometers per hour. We can see also the spike in the average moving average speed. And this is the findings for 15 kilometers per hour. So this table compares ground truth measurements between the UWB estimation and the ground truth data from the camera. The table shows the absolute difference in distance is 0.88 meters. The absolute difference in speed 0.46 meters per second, and 1.1 in time to collision. The study looked at various classification performance measures such as sensitivity and specificity to evaluate the performance of the UWB. Specificity and sensitivity were calculated based on the true positive and negative rates. Sensitivity, the blue line, measures the ability of UWB to correctly identify high-risk scenarios, true positives, where the time to collision is less than the threshold, which is 3 seconds. Specificity, the orange line, measures the ability of UWB to correctly identify safe scenarios, true negatives, where the time to collision is greater than or equal to the threshold, which is 3 seconds. We can see also the algorithm that was used, for example, in calculating the moving average speed, distance, modified time to collision, mixed time to collision. And now back to Dr. Karim Ismail.
Thank you, Salah. Another way to measure proximity between two road users is through a very commonly used indicator called post-encroachment time. And it's especially used in pedestrian safety. So before we measure post-encroachment time, we need to understand what it represents. So if you have two road users and they have already moved, and we want to know how risky such interaction was. So we would record when they enter a specific zone, for example, where their paths intersect, and then when they exit from such a zone, and then we calculate the time that elapses when one of them, between the moment when the earlier of them left and the later of them joined. And that time represents, a measure of how close they are. So that's why we call it retroactive proximity. It's the movement has already been completed. In contrast with what Salah presented earlier, where predictively we ask how far are they from collision. We need to have a good definition of what a conflict zone is. Is it a point in space, or is it, it has width and length? And how are we going to check in and out road users from such zone? So an important measurement that needs to be done is the occupancy time. So how long does one road user stay within a conflict zone? Can we do this using wireless sensors? Because you can do them using cameras. Can we do this? Can we measure these time durations using a wireless sensor, specifically in our case, ultra-wideband sensor? So I will move the presentation to Salah to explain the technical details of the experiments he did.
Thank you, Dr. Karim. So this study aimed to examine the performance of UWB sensors in detecting the time proximity between two tags as they cross each other's path. The experimental setup and the used equipment are shown in the figure. So 4 anchors were used in the experiment to estimate the position of the UWB tag. The anchors can be placed at fixed locations, preferably in a grid pattern, by attaching them to a stable structure. The UWB tags can be attached or hauled to a moving host, such as a vehicle or pedestrian. The range of the tag measured relative to the anchor position is calculated in terms of the signal time of flight. In this study, each anchor was affixed to a stable mountain device at a height of 0.9 meters or 90 centimeters. So each anchor communicates with a nearby tag to range the relative distance between them. This creates the time sequence of distance measurements for each anchor tag pair. In the early stages of the experiments, the distance data acquired by the tags were uploaded to the cloud based on the storage every 200 milliseconds. This method was adopted because uploading data too often could result in loss of data packets. Later, we found the best way to send the data to the cloud was by batches. This modification allowed for a longer time between instances of uploading while maximizing the number of captured detections. We did apply some time synchronization methods such as master-slave synchronization using a third tag, synchronization with a global time reference, and we looked at the tag's clock. So, for example, once an anchor communicates with the tag will be responsible for reporting the time of flight calculations, the timestamps. The tag has two options for reporting measurements. The first option, the measurements can be sent to the cloud through a tag's LTE modem. For example, it will send to the nearest tower, it will print the global time and then send it to the cloud. Or option two, the tag can be paired to a laptop through Bluetooth Low Energy, and the laptop upload the measurements to the cloud through the internet. The tag will choose the fastest path for uploading the measurements. There is a third option of synchronization, which is master-slave synchronization. We added a 3 tag. It's paired through Bluetooth with a tag. And then it will, the third tag will broadcast or advertise the timestamps. The tag number 2, which is in the experiment, it will scan for the timestamps, print it, and then it will choose one of the options to upload to the cloud. First, we looked at static experiment was conducted with a 10 by 10 study area. A tag was set up at a reference point, for example, 3 and 5, which is point of a conflict zone that was outlined. The UWB tag was attached to a selfie stick at 0.65 meters in height, as shown in the left figure. These are some findings where we looked at each trial we placed the tag at each point. We found that trial 2, which is point 3 and 5, there is some, the mean average error was higher than the other trials. We looked into that, and we found it was observed that the anchor located at 10 and 10 provided a wide range of distance detections. Although the actual distance between the anchor and the stationary tag was 12 meters, the distance measurements reached to 19.5 meters, as shown in this graph. We also looked at tags orientation, if it's supposed to be in vertically or horizontal. So this table shows the detections distance ranging between the tag when the tag is vertical. And we place the tag at each reference point, for example, 1, 3, 5 meters to 20 meters. After analyzing the data, we looked at, we found that at 17 meters, it was repeated twice as shown, and we can see it's very high mean average error. When we looked at that, this graph shows the distance measurements at 17 meters. It was found a multi-path issue and different time of flight calculations. And when the tag is placed as horizontal, we can see that the anchor cannot detect the tag after 10 meters. Then many dynamic experiments were conducted to measure the position and movement of moving objects, such as the skateboard, which represent a vehicle or moving object, and the pedestrian. So 2 tags were attached to a selfie stick, one held by a pedestrian and the other one attached to a skateboard. We also looked at increasing the number of anchors. For example, instead of 4 anchors at each corner, no, we looked at 8 anchors to see if we will have a better distance measurements. So dynamic experiment, as we can see in this figure, we can see that the pedestrian entered the conflict zone, exit, and then the skateboard. We found that this table displays a comparison between the timestamps of ground truth data from the camera and the UWB tags when entering and exiting the conflict zone for one tag. So in this case, the other tag we couldn't find, or we couldn't detect any detections just from one device. And the mean absolute difference in time occupancy was 0.43 seconds. Then we said, okay, let's look at one tag only, one object. It was observed that the time occupancy difference, the absolute difference, is 0.05 seconds for an 8x8 meter study area. We did the experiment again to see, because the difference between 0.43 seconds with 2 tags and this one is 0.05, then we repeated the experiments and we found it's 0.08 seconds. Then we conducted a larger study area, 15 by 15 meters, and the time occupancy difference between the ground truth and the UWB was 0.36 seconds. After that, the experiments divided the network into 2 independent PAN IDs, or personal area network identifiers. For example, each 4 anchors will communicate with one tag, and the other 4 anchors will communicate with tag number 2, as shown in this figure. After investigating the tag's trajectories, we were able to have now some detections from the second tag, but it was found that tags were affected by signal interference that resulted in gaps in detections and inaccurate distance measurements. For example, if we look at the trial number 16, the pedestrian supposed to move from south to north from point X at or 0 and 4 straight to the 8 and 4, but we can see that we have some measurements that affected by signal interference. And now I will let Dr. Karim to present some limitations about the U1 chip.
Thank you, Salah. So as with any technology, there are shortcomings and also opportunities for improvement. This is really, work at early stage, and the technology needs to improve at hardware and also at algorithmic levels. So right now, we used only the U1 chip, but we didn't have a chance to use the U2 chip, which promises many improvements, including superior range. Salah discovered many shortcomings in his work, and improving range can definitely add value to the measurements. Salah discovered some shortcomings when multiple tags are used, and it seems to be a challenge that needs to be taken seriously if multiple tags are to be tracked. Salah, next slide. Also, as I mentioned, interference was noticed. There were some lag in signal communication that can happen sometimes randomly. Synchronization is a common shortcoming, and there are many solutions to it, but Salah attempted a few techniques to address this issue. We also should include more experiments on non-line of sight conditions where there is an object between the beacon and the receiver. And many experimental settings were idealized. Some of the conclusions may be specific to our experiments. Salah tried to introduce a third tag in his experiments, and we noticed some shortcomings in the performance. Future direction, we would like to do so many things. Most likely, as far as Salah is concerned, it is beyond his PhD, but the technology is new, the hardware is new, and there are so many new questions. Can we reliably track more than one tag? Can we calculate post-encroachment time in a reliable fashion? How can we alert the driver? And how much time will it take for a real alert to be sent to the driver? And how is that going to be done? Can we utilize such technology to collect cross-sectional data? For example, many users at one site. And many other shortcomings that we would like to address as also identified in our publications. So at this stage, given the time, I think I'm gonna open the question now for the floor to ask us, the audience to ask us questions. These are the publications by Salah and myself, and thank you very much for your time.
Well, thank you so much. Excellent presentation by both of you. It's very exciting, this new area of technology that you're exploring. And as you said, the fact that cell phones are ubiquitous, it makes sense to explore ways that we can use those to detect pedestrians. So I'm going to invite people from the audience to submit their questions. In the meantime, I do have a question myself. I was just curious how I believe there are pedestrian detection systems out there with like possibly machinery. Like I just happened to do a quick Google search, and I guess there's some forklift machines that have that, and some cars have pedestrian detection. And I'm just curious what kind of methodology they use and how that compares to what you're exploring and how yours is different. And either of you.
I will give Salah also a chance to answer.
Yes.
Go ahead, Salah.
Yeah, thank you, Dr. Karim. So this technology is, I know there are other alternative technologies, and they are robust, but as we mentioned earlier, for example, when we have a foggy weather condition, the cameras cannot detect pedestrians. So in this case, ultra wideband or wireless sensor can detect other pedestrians.